All right, so chapter 3 is when we really start to get into the thick of organic, right? You have been through chapter 1, that was largely review from Chem 1550, Chem 1560. You got into chapter 2, some of that was new, like predicting where equilibrium lie. Does it go to the left, does it go to the right? But other than that, largely still new or old ideas. We learned some functional groups like carboxylic acids and alcohols, but you knew the definitions of acids and bases, right? Bronsted, Lowry, and the Lewis definition. Okay. But chapter 3 is the first truly brand new chapter, which is why you see its name, right? An intro to organic compounds, where we're going to learn about nomenclature, how to actually name these things. There's a whole new system on top of what we learned how to do in Gen Chem. We're going to spend a video talking about physical properties, another one talking about structure, and then we finish the chapter talking about cyclohexane and its different conformations. So we're probably looking at 5 or 6 videos in total for chapter 3. And I don't actually know how the video will show up like this, but I've also got Caleb with me on this video today, who's going to address any questions moving forward at the end. So chapter 3, what are we thinking about moving forward for pretty much every single chapter moving forward in organic? Okay. I've alluded to it already in the earlier chapters, right? Organic chemistry is kind of synonymous with synthetic chemistry. A lot of people who get graduate degrees in organic chemistry go on to become synthetic chemists, because it's kind of a different way to think about something you already know. When something undergoes a reaction, in the past we've seen that it goes from reactants to products. Okay? But how we're phrasing that in organic is when your reactants are reacting, we are synthesizing something else. We're making a new product, which is what synthetic organic chemistry is all about, right? We are going to begin in the next couple of chapters learning how compounds react, but then we're also indirectly, by learning how they react, learning how to make new things. But before we can do any of that, the whole purpose of chapter 3, at least this first half, is to know how to name them. And we are going to get 5 functional groups, kind of 5 families of nomenclature in this chapter. We're going to learn how to do alkanes, okay, alkyl halides, ethers, alcohols, and amines. Okay, so 5 new families for this chapter, and then we'll get into other ones in later chapters. Chapter 5, for example, is all about alkenes when we're doing alkanes this chapter. Starting on this slide right here. Slide 3, we get our first big table, table 3.1 from your textbook. Okay. Alkanes we've already defined in the past, right? It's a hydrocarbon, meaning it contains only carbon and hydrogen. They're saturated, meaning they only contain single bonds, right? Something is unsaturated if it has double or triple bonds. But here we've got saturated straight chain alkanes, meaning everything is just in a straight line of carbons. And they have the general molecular formula CnH2n+2. See on the top right here, you should make sure you jot down that formula. You need to know it for alkanes, alkenes, and alkynes to quickly predict what you've got. So CnH2n+2, where N is an integer. That gives you the molecular formula for a straight chain alkane. No branches, no rings, nothing else. And what you need to do from this table, 3.1, is memorize the first 10 names. This is the whole foundation of nomenclature, knowing how to name these alkanes. So you should quickly know that methane means 1 carbon, pentane means 5 carbons, okay? Nonane means 9. And there are, as you see on this next table, right, names for the higher number of carbons as well. I don't expect you to know anything from slide 4 here, but slide 3, I do expect you to know these first 3 columns. Okay, the number of carbons, the molecular formula, and the name, methane through decane. And we'll talk about the physical properties in a later video. So memorize the names for those first 10 alkanes. And the reason that I can put them into a family and just call them all alkanes, in addition to having the same principles for nomenclature, they are known as a homologous series. Okay? A homologous series, or these 2 molecules that are shown on this page, propane and butane, they're homologues. Okay? A homologous series of alkanes or two molecules that are homologues, which means they differ by just a single CH2 or sometimes several CH2s, which is called a methylene group. CH2 is called methylene, whereas CH3 is methyl. Okay, so they differ by just one methylene here. Right, see these two, just a different CH2. They make up two homologues in a homologous series of alkanes, which we've already talked about, all have the same general molecular formula. Okay, so that'll allow you to quickly identify when you have an alkane. We've already talked about the nomenclature, okay, in that first table. And for the first three, it's easy. Okay. Methane, ethane, and propane. They can only bond one way. They're straight chain carbons by definition. Okay. But butane, however, can form two different types of butane, two isomers that are both C4H10. And you see one of them right here, down at the bottom. All four carbons in a row fill in the hydrogen so that every carbon has four total bonds, sp3 hybridized. But there's another way to make C4H10 as well. And I recommend you pause the video here and try and figure it out. Okay. Where else can you put a carbon to make C4H10? Okay. And hopefully you come up with this guy right here, which is called isobutane. So notice the two ways that we can arrange C4H10. One is called butane, the other is called isobutane. And I mentioned they were isomers before, but as we move throughout chemistry, specifically in chapter 4, we're going to have different types of isomers. And these two are called constitutional isomers, which means they have the same molecular formula, but the atoms are connected to one another differently. And that's the original type of isomer that we learned in Gen Chem 1, constitutional isomers. Same formula, bonded differently. And you want to get familiar with this group right here. Okay, when you identify this group in yellow, you see it over here in isobutane, a carbon that's connected to one hydrogen and two methyl groups. Remember, CH3 is methyl. That's called an iso unit. And sometimes that's used in nomenclature because it gives us the isobutane name. It also gives us isopentane, okay? Because there's three different ways that we can arrange C5H12s. One where they're all in a row, that's just normal pentane. Another one where I take that methyl group and move it down over here, that's isopentane. And then a third way where I have two methyl groups branching off of the middle carbon. That doesn't get a special pentane name, it's just called 2,2-dimethylpropane. And don't worry, we're going to get to that naming protocol shortly. Okay. And as you continue to grow these things, right, there's more and more ways that you can put them together. So if I go to hexane, right, that's one isomer of C6H14, but there's 5 total isomers of hexane. Okay. And then if I go to 7 carbons, now there's 9 different ways that I can arrange that. If I go to 10 carbons, there's 75 different compounds that I could make. If I go to 15 carbons, only 15 carbons can make more than 4,000 different isomers, right? So there's this huge exponential jump. And it would be ridiculous to give them all a unique name. And that's why we have a system of nomenclature in chemistry, right? It's a set of rules for creating systematic names that describe a compound's structure. Okay? And what we're going to use is IUPAC nomenclature, International Union of Pure and Applied Chemistry. It's the same set of rules we use in Gen Chem. And that's all you have to learn, right? Is the IUPAC rules. You don't have to memorize any names except for those first 10 that I gave you on the previous slide. Okay, that's a basis to start. After that, if you learn the rules, you'll know how to name anything. And these are different from common names. Okay, so when we jump to the next slide here, where we start to look at how we name alkanes, they're different from common names, okay? Common names, all right, there's none here. All right, common names are what are here in red, and you do not have to know common names because there's not a set of rules that are as clearly cut. So while I will use common names throughout the course, you're not responsible for memorizing them. You're going to indirectly learn some of them anyway. You probably already know some of them. okay? But a common name would never appear on a test, for example. The test will have systematic IUPAC names. Okay? So what are those rules? How do I name alkanes? Okay? We already saw it with 2,2-dimethylpropane. That was the first place we saw what's called an alkyl substituent. Okay? An alkyl substituent is just an alkane with one fewer hydrogen. Okay? So take a hydrogen off of an alkane and it becomes an alkyl group. And I name it just by dropping the ANE from the alkane and replacing it with YL. So methane, CH4, becomes methyl, CH3. Pentane, which was, right, we saw C5H12, drop an H, it becomes C5H11, pentyl, right, pentane to pentyl. And that's why you have to know those first 10 alkanes, because you drop the ane off the alkane, replace it with YL, then you've got a name of a substituent. Again, it's all based on those initial 10. Okay, and these, right, won't change reactivity all that much, methyl, ethyl, propyl, butyl, pentyl. Okay, so generally we see these in chemistry pretty frequently. We've already talked about this in the review session, right? You see those just represented typically as an R group. So if you see R in organic, it's just a general alkyl group. Okay? But if you replace that hydrogen with something else, then you can get a functional group. Okay? And these are the functional groups that I alluded to before. If we replace the H with an OH, then now we've got an alcohol, or NH2, an amine, or a halogen, we get an alkyl halide. Or if we put an oxygen in the middle, that's called an ether. And we can get common names of these things just by naming the alkyl group followed by the class of compound, right? So methyl group, OH, alcohol. Methyl alcohol is the common name versus methanol, which is the IUPAC name. Okay, propyl group followed by NH2, which is an amine. Propylamine is the common name. Okay, name the two alkyl groups and then say ether, as long as the alkyl groups are in alphabetical order. Those are easy to name. Okay, but those are the common names, right? We're thinking about the IUPAC name. So common name, alkyl group, followed by class of compounds. There's typically a space, except for amines, there's no space. Okay, ethers, list them alphabetically. I mentioned all that on the previous slide. But you see, subtle stuff like this is why common names can be tricky. And we're going to be worried about IUPAC names moving forward. Okay. But for some substituents, just like we saw with butane, where there was two ways to make butane, right? What about if I start with propane and I pull off a hydrogen? Okay. Depending on what hydrogen I pluck off, I could get a different group where that bonding is going, right? If I pull one off the end, it's called a propyl group. But if I pull it off the middle, it's called an isopropyl group, because notice it made that iso group again. Okay. And the difference is what kind of carbon it's bonded to. Okay. You might first be thinking, well, what if I pull off the left-hand hydrogen over here? Well, that's not actually different, because remember in organic, we have to think about things in 3D. And if I just take this propyl group and flip it 180 degrees, right, it's the same thing. But it's not the same as pulling the hydrogen off of the middle. And the type of carbon, right, here in the middle, this is called a secondary carbon. It's bonded to two other carbons, the secondary carbon, versus this carbon is only bonded to one other carbon. So that's called a primary carbon. Okay. So we're going to use those terms later on, but this is a good place to introduce them, right? A primary carbon is bonded to one other carbon. A secondary carbon is bonded to two other carbons. A tertiary carbon is bonded to three other carbons. So what if I look at 4? Carl, I'm actually getting ahead of myself. I forgot this slide was in here. I was describing it all before, right? Here's all the information. Perfect. On slide 18. Okay, primary carbon, secondary carbon, tertiary carbon. And I guess and yeah, hydrogen follows the same set of rules because the hydrogens are named off of the carbons they're bound to. Okay. A tertiary hydrogen is just a hydrogen that goes to a tertiary carbon, for example. Okay. So great. So forgot that slide was in there. Know that moving forward. So one other thing to pay attention to, and again, harping on the fact that we need to always be thinking about things in 3 dimensions, okay? Notice here, 2 different structures that at first glance look different, at least on paper, but they're the same in the real world in 3 dimensions. Right? Thinking about the fact that carbon is tetrahedral, right? Taking up the 4 corners of a tetrahedron, it's sp3 hybridized. So you can rotate this around, right? Spin it around here, match up the green chlorine, for example, and get the same compound. That's a really common area of confusion early on in the semesters of Organic 1, right? These are not isomers. They're the same thing. You just took this and kind of rotated it up. Same molecule, still isopropyl chloride, still got the same iso group, chlorine still bonded to the same carbon in each situation. And this is one of those situations where modeling kits, which I recommended you purchase, are going to be a really big help to see how those are the same, right? Thinking about them in 3D. And if I go from a propyl group to a butyl group, now, right, there are 4 different ways that I can form a butyl group, right? Just pulling it off the end of butane, okay? Or I could have pulled it off the end of isobutane, or I could have pulled it off the middle of butane, or I could have had, right, this other situation where I've got these 3 methyl groups bonded to carbon and I plucked the hydrogen off the middle. And those give me the new names of these substituents. If it's just plain, right, C4H9 here, it's a butyl group. Isobutyl has the iso group right there. Okay? Isobutyl, it's the only way to make a butyl group with an iso unit in it, isobutyl. Sec-butyl comes from the fact that this is a secondary carbon. Tert-butyl comes from the fact that this is a tertiary carbon that's bonded to the molecule. So you should know those as well, right? No propyl and isopropyl, no butyl, isobutyl, sec-butyl, and tert-butyl. Yep. And the reason that we get different names is that they specify different substituents that are bonded to a molecule. But sec-Pentyl is a crappy name because sec-Pentyl means that my substituent is bonded to a secondary carbon. But there's 2 different types of secondary carbons in pentyl, right? One right here and then one in the middle. I'm not counting the one that's over here because it's the same as that, thinking about it in 3 dimensions. So I can't use sec-Pentyl because there's 2 types of secondary carbons in a pentyl group. So that name doesn't apply. I can do tert-butyl and I can do tert-pentyl because I can still make a there's still only one way to make a tertiary carbon in a pentyl group. But after that, things kind of fall apart. So make sure that you know, right? Not for Monday, it would have been Monday if this was a normal semester, right? No isopropyl and normal propyl, no isobutyl and butyl, no normal pentyl, sec-butyl, tert-butyl, and normal butyl, and then tert-pentyl, which has a typo there. Actually, I got to fix that. Tert-pentyl, sec-pentyl, or sorry, there is no sec-pentyl, normal pentyl. Okay? So to rehash that one more time, because I definitely did those out of order: propyl and isopropyl, butyl, isobutyl, sec-butyl, tert-butyl, pentyl, and tert-pentyl. Those are all of your alkyl substituents that you will have. And remember, you've got the rules to help you. You can identify the iso group, right? Showing again here in orange or yellow, depending on what your screen resolutions are set to. And you can also find them, right, by identifying if it's bonded to a secondary carbon or a tertiary carbon. You can think about the iso group like being a little Y, right? Capital letter Y branching out. And that's all summarized here in table 3.2. Okay. You've also got hexyl and isohexyl, which I do not expect you to know. You're going to learn them indirectly by learning the rules, right? But the rest of the alkyl substituents you have to know. That's the big takeaway from video 1, as well as the first 10 alkanes, right? Methane through decane. You have to know those moving forward, because in the next video, we are going to continue these ideas in naming other organic compounds.